Okay, well, welcome to lecture 9. Today I want to sort of do a side trip here and talk about something called the Lorenz model. This is like an application of something from physics, something that comes up when we're solving these dynamical systems, these coupled sets of equations. I want to tell you a story. And so this story, if you might have read it, I don't know if you've read a book from 1987, but I remember reading this book back somewhere in the early 90s. This book called Chaos. It's by James Gleick. And so this lecture is adapted from chapter 1. Basically, if you want the written version, I encourage you to go take a look, but I think it's a good story. So one of the quotes from a great physicist, a guy by the name of Richard Feynman, is physicists like to think that all you have to say is, here are the initial conditions, here are the conditions, and now what happens next? In the sense of, if I could just write down the equations of motion and give you initial conditions, I could solve whatever's going on, right? We've done this with the projectile motion problem. Give it the initial velocity, give it the initial position, you predict the behavior. We've done this with oscillators. Give it the spring constant, the initial displacement, you can predict the evolution of the oscillator. We've done this with various things with drags and spinning balls. And the idea is, assuming you have the physics correct and you have the right initial conditions, you can predict the evolution of the dynamical system. Here's another quote by a fellow named Ed Lorenz. When a butterfly flutters its wings in one part of the world, it can eventually cause a hurricane in another. So you might be familiar with this particular phrase. That's where it comes from. The phrase butterfly effect. I'm going to talk to you about the butterfly effect and how this relates to solving equations numerically. Okay, so first of all, Ed Lorenz. So that's this fellow right here. This is obviously taken later on in life. Earlier on in life, Ed Lorenz was working at MIT. James Gleick writes, "The sun beat down through a sky that never had seen clouds. The wind swept across an earth as smooth as glass. Night never came, and autumn never gave way to winter. It never rained." The simulated weather in Edward Lorenz's new electronic computer changed slowly but certainly, drifting through a permanent dry mid-season, as if the world had turned in Camelot, or in some particular bland version of Southern California. Okay, so who is this Ed Lorenz guy? So Ed Lorenz is a meteorologist. He's studying how to simulate the weather. We're down in the 1960s. Here is where he's doing his work. Computers in the 1960s were not quite as fast as what you have in front of you. They were not quite as fast as what you may have in your cell phone. They sort of looked like, well, that's the computer that was in Ed Lorenz's office. It's sort of a machine. It's what that big box is right there. And you communicate it by typing stuff in. And it communicates back with you by typing stuff out. You see that little ticker tape there on the left-hand side? Well, so that's how it's communicating in or out. So not the best user interface, but it had a way of controlling it. It didn't have a lot of memory, didn't have a lot of processing power. So if you were going to simulate the weather, you had to make a few approximations. Number one, let's get rid of those clouds things. Clouds are tricky. By the way, clouds are still tricky. We do not simulate clouds correctly in weather models. Oceans are pretty important, but let's not deal with oceans and air. Let's get rid of the oceans. So land everywhere. We have to adjust for we have really limited memory and limited speed on this thing. So let's make a toy model of the climate. And how I'm going to actually display what the measurements are in my model of the climate or the weather in this computer model is going to be by printouts. Basically, you're going to look at temperatures and pressures at various spots on a globe. You can imagine on Earth, which is perfectly smooth, there's no clouds everywhere, and we just want to know how the temperature and the pressure change over the surface of that globe. And that's what Ed Lorenz was looking at. Okay, so the thing about his program is it wasn't so much as set the temperature of the sun and look what the equilibrium temperature of the planet was. This program that he wrote, based on physical principles, conservation of energy, conservation of momentum, would have some variability. It would have variability that looked like the sense of the character of real weather variability. Every minute, the machine marked the passing of a day by printing a row of numbers across a page. And if you knew how to read the printouts, you would see a prevailing westerly wind swing from north to the south and backing into the north. Cyclones spun slowly around an idealized globe. As the word spread through the department, other meteorologists would gather round, along with graduate students, and make bets on what Lorenz's weather model would do next. Somehow, nothing ever happened the same way twice. Okay, so this is a nice toy model allowing you to simulate the dynamics of a weather-like system. And it wasn't just like it was hot, cold, hot, cold. It sort of did things like weather does. I know that generally it's going to get warmer in the daytime and cooler at nighttime, and it'll be colder in the winter and warmer in the summer. Lorenz's model didn't have any of those forces. It just was the temperature of the afternoon. It was always the afternoon. And yet, the temperature would go up and go down, and the winds would blow stronger and blow weaker, like weather does. Now, just some names, with of course, we know a lot about climate change, and you've heard about these things, just so we're on the clear page. When we're talking about weather, we're talking about the variations in what you actually experience in measurement. You're talking about the patterns and the distribution of temperatures and the pressures and of winds. Climate would be the averages or the long-term trends of the weather. So if you take the mean average temperature in the winter, it is always going to be colder than the mean average temperature in the summer. That's a climate statement. The weather would be what is the instantaneous temperature somewhere else. And climate, at least until it starts changing, can be talked about in terms of averages. If not true averages, then 5-year averages, 10-year averages, 30-year averages. You could talk about norms. Weather didn't appeal to the statistical kind of thing. You couldn't say the average temperature was 12 degrees and have that in any meaning. It was more variable than that. Weather had a flavor that could not be expressed by talking about averages. The daily high temperature in Cambridge, Massachusetts averages 75 degrees in June. Well, that's great to have a statement like that, a climate statement, but you want to know what the temperature actually is every particular day for all different months of June. And the thing about Lorenz's model is it captured the essence in the way that the patterns of the atmosphere changed over time. You had those structures in an equation. How did he come up with this? Where's the basis of this? What were the equations of motion for this model? Basically, they were just 12 simulated numerical rules. Okay? We've been doing equations that look at 2 numerical rules, as in the change in position is equal to velocity. The change in velocity is equal to the sum of the forces. When we talked about balls that were spinning or moving in multiple directions, we had 6 equations. What is the change in the velocity in the horizontal direction? What is the change in the velocity in the vertical direction? What's the force in the horizontal direction? What's the force in the vertical direction? Right? You can imagine writing those out as a system of equations. Well, he had 12 equations like this. And what they were is equations derived from fluid dynamics and thermodynamics, relationships between temperatures and pressures and wind speed. If you have a pressure difference, if the pressure is high in one place and low somewhere else, you're going to get a wind between them. The whole planet is rotating, and so you bring rotation to that effect, and there's some Coriolis forces and some that tend to deflect the winds to get cyclones and other kind of structures. You want to have the model respect conservation of energy, conservation of mass, conservation of momentum. So you can imagine, and I won't write them down, but you can imagine writing down a set of 12 equations that satisfy this particular set of stuff. Now, this is a Newtonian approach. The idea is if I could just write down the equations we're dealing with, then through the determinism of physical laws, I can use them to predict what the system is going to do, and hence what nature is going to do. Those who made such models took for granted that, from present to future, the laws of motion provide a bright mathematical certainty. Understand the laws, and you understand the nature, the universe. That is, or that was, the philosophy behind modeling weather on a computer. So this was the idea and the thinking in the early 1960s. If we could just write down the right equations, we could solve numerical weather predictions. We could figure out what the weather was really going to be next week, next month, next year. Now, I'll tell you a little bit about Edward Lorenz. Okay, so Edward Lorenz, he was always interested in weather, mathematically gifted, so he had an affinity for mathematics. And in World War II, he was a weather forecaster for the Army Air Corps. That experience working meteorology during the war led him into a career in meteorology. And what he was working on as a researcher at MIT was the general theory of how the atmosphere works. Why do we have atmospheric circulation? Why is there a jet stream? Why do hurricanes travel the paths that they do? But in the back of his mind, one of his interests was weather forecast, right? So the idea of trying to figure it out. Now, in the 1960s, if you think about the weatherman not being able to get the weather right today, in the 1960s, really bad, right? In terms of a weather forecaster, other than telling you what the weather is right now, my ability in the 1960s would tell you with any degree of certainty what the temperature is going to be 2 or 3 days from now. Very, very poor. We had very, very poor skill back at that time. We still don't have great skill, but we're pretty good to about 5 or 6 days. We can tell you the temperature, what's going to be early of next week, and we tend to trust that. Can't tell you what's going to be 2 weeks from now, but a couple days out. But in the 1960s, meteorology didn't really mean as a science. It didn't include forecasting, right? It was mostly guesswork. What you would do is you would look at a map, and you'd look where the high pressure was and the low pressure was, you know where the winds were going, and you went, okay, things in motion without forces tend to keep going in motion. So the high pressure ridge was 500 kilometers away and it's traveling at 1 mile per hour. 500 hours from now, that's where that high pressure ridge is going to end up. So it's just deterministic, right? You look at maps, you're drawing arrows, and it was a technical thing, not a scientific thing. Science in meteorology, capital S science, favored problems that had exact solutions. Things that I could write the equation down, and then with pen and paper, well, marker, chalk and blackboard, I could write down the solution. That's what scientists would do in meteorology. Computers, and we're at the early 1960s here, were not yet an essential tool for doing science, for doing theoretical science. Today, they definitely are, but was not the case at that point in time. Computers are viewed as souped up calculators, right? They're basically just doing the calculations you could do in person. And you might be familiar with this kind of story. Prior to about the 1960s, you could have an occupation. Your job could be a computer, a person who did calculations all the time. So there's a few movies around that kind of idea, right? The idea you have cores of people, and I just come up with equations, and I hand it to you, and I say, okay, calculate these numbers, and do it again and again. Computers, in our modern sense, just automates the manual human computers. But there's some advantages. Computers can do the arithmetic, that adding, multiplying, dividing, pretty fast, and they were always getting faster. And if you could do the computation fast enough, maybe you could write down equations that couldn't be solved analytically, but maybe you could solve them numerically. And just maybe we could make weather predictable. This is sort of the promise of the zeitgeist of the era. Okay, let's do a comparison to another branch of science, astronomy. Okay, so astronomy is well established at this point. We've been staring up at the skies for a long time. We've got an understanding of where things are in the sky. We name them, we see when they're coming. We've got observations of when things appear, when things disappear. A long time, this guy called Isaac Newton, he comes up with a theory of gravity. He comes up with laws of motion and goes, I got it covered. I know why the things up there are doing what they're doing. They're doing because you've got a gravitational force and we've got all the planets rotating around the sun. And I can use that mathematical formalism to make predictable rules that describe how the mechanics are going to behave. And we can do this for planets, for comets, and for tides. And if I could write down equations for how the molecules of air and water are described and how they interact and how they work, like we do for planets, all the physics, we have all of the physics we need to be able to solve the equations. There's no new physics that needed to be discovered in the 1960s to understand how air and water and heat work. Classical physics works for all those things. There's no quantum effects. You don't need to worry about relativity or anything complicated. It's all in there in basically 18th century physics. Now, astronomers never made perfect predictions. There was always extra perturbations you could make. If you're trying to study the motion of the planets, you'll start with a few of the big planets in the sun. But there are other planets that will perturb the motion a little bit. There's a little gravity from all the little moons around the planets and all the asteroids as well. But those are corrections, small perturbations to the main solution. You were pretty close. So if you made a prediction like Halley did, that the comet named after him, Halley's Comet, We'll come back in 76 years. You could be relatively confident that 76 years from now, a comet in the sky, you go, oh, look at that. There's a comet. Well, I've been watching it come, and it's been coming every 76 years, and I understand its orbit, and I understand its speed, and how far away it goes from the sun, and I know about gravity. I can calculate that it will return back and visit the Earth again around 76 years later. Now, it may not be 76 years exactly. It could be 76 years and 1 month and 4 days. Maybe it's 76 years, 1 month and 5 days. But, you know, I'm close. I'm pretty good. Now, if it worked for comets, like it works for spacecraft, remember we're in the space age of the 1960s, and it works for missiles, we're in the ballistic age, sort of the Cold War, why wouldn't it work for winds and for clouds? So here goes the thought. Weather was definitely complicated, right? And unlike throwing a ball up and having it go up and coming back down and hit the ground, weather, with all of its winds and temperatures and temperature gradients, pressure gradients, right? You've got a lot of things going on all the way through. But the equations are still Newtonian mechanics, F equals ma at their core. Doesn't this mean that weather should be predictable? Here's some science philosophy for you. I'm talking about a guy named Laplace. Laplace, the 18th century philosopher mathematician who caught the Newtonian fever like no one else. He imagined a character, now called Laplace's demon, such as an intelligence, Laplace wrote, would embrace the same formula, the movements of the greatest bodies of the heavens and those of the lightest atom. For it, nothing would be uncertain, and the future, as the past, would be as present to his eyes. So the thought is, what Laplace is writing about is you could imagine writing down the equations and solve them fast enough, you would be able to predict literally the future, what would happen. If you just knew what was going on right now, you could iterate those equations and figure out what the weather is going to be for any day into the future, right? Now, we do have things like relativity, which is predictable. You do have things like Heisenberg's uncertainty principle in quantum mechanics. It tells you that you're never able to predict things in terms of precision of position and velocity or position and mass down to a really small scale. But as long as we want to do something better than 10 to the minus 23rd, which is pretty good, most of science has pursued this dream of trying to reduce down all issues of science into fundamental principles that you can solve, evaluate, mathematically compute, predict. So the idea, the theory of science is what we're going to do is describe the universe. Now, the universe might mean whatever it means. To an astronomer, it would mean equations of gravity. To a biologist, it would be the equations of biology, the equations of evolution. For a neuroscientist, if I could just write a model for what every one of the neurons in your brain was doing, I could solve what your brain was doing. For economists, if I could just figure out the equations of how the economy worked, I could get very rich because I could predict exactly what it was going to do. I could solve the equations for the stock market. That's the thought. This view of Newtonian determinism had been intermingled with computing ever since John von Neumann designed his first machines at the Institute for Advanced Study in Princeton, New Jersey in the 1950s. Von Neumann, who's like a godfather of computing, recognized that weather modeling would be an ideal task for a computer. Okay, so this is the thought, right? In the zeitgeist is we can use these computery things to maybe predict the weather, right? Okay, and we're going to make a little compromise here. We know that measurements are never perfect. If I grab a thermometer, I measure the temperature, I'm getting it within a measurement error. I'm not getting it to an unlimited level of precision. But the assumption here is if I only want my temperatures to be accurate to within 0.1 degree, I don't really need to measure anything better than 0.1 degree. Here's the assumption. Given an approximate knowledge of a system's initial conditions, and of course the understanding of the natural laws, the laws of physics, one should be able to calculate the approximate behavior of the system. The basic idea of Western science is that you don't have to take into account the falling of a leaf on some planet in another galaxy if you're trying to account for the motion of a billiard ball across the pool table here on Earth. Small influences, especially very small influences, are neglected. There's a convergence in the way things work, and arbitrary small influences don't blow up to have arbitrary large effects. That's the inbuilt assumption here in Newtonian determinism. So the example I'll give you is of Halley's Comet. So let's say you had a tiny measurement error in the observation of the position when Halley Comet came to visit in 1910. Well, if you were off by a little bit, angle of right ascension and whatever I'm not an astronomer, but the two directions of where something is, you had a small error in that observation. You'd only really have a small error when it arrived again in 1986. And that small error would remain small for millions of years to come. Another example would be computer guidance systems, right? You would actually go and take a look at what the Apollo spacecraft's source code looks like. It's all uploaded to GitHub now. But the idea is we're able to control things like spacecrafts, and we're never perfect. You never can turn on the engine or turn it off at exactly the right moment, but we're pretty close. And with pretty close, you can get pretty close to like the moon. So approximately accurate input gives you approximately accurate output. And if you were an early pioneer in global weather forecasting, you assume the same principles. Well, you're gonna have some errors, but how bad could those small errors be? Okay, Lorenz's weather model. I'm gonna go back to this. What he had done is he had reduced weather down to its most essential elements. You have the conservation of energy and mass and momentum. You have to have the equations going on. It's just a skeleton. It gives you a character of what weather was there. But the essence was there. There were winds and there were temperature, and they were behaving as you looked at the numbers being printed off of this machine in a recognizable, earthy kind of way. And it matched our intuition about weather. Something that repeats itself. There's cycles, there's storms. It would come and go. The pressures would go up and go down. And Lorenz started to notice some patterns in his data. He'd start noticing that when a line went from high to low, as in the pressure went from high to low without a bump, a double bump would come next. High, low, and then high, low, high, low. Well, maybe these were some rules we could discover. Maybe there was something that a forecaster could use, that there was some pattern in the oscillations of the weather. Maybe if you just ran the model long enough, you'd see that there were cycles or patterns or things that you could use for prediction. There was disorder, but maybe it's an orderly disorder, something you can infer. One day, 1961, Lorenz takes a shortcut. One day in the winter of 1961, wanting to examine one sequence at Greater Lake, Lorenz took a shortcut. Instead of starting the whole run over, he started midway through. To give the machine its initial condition, he typed the numbers straight from the earlier printout. When he walked down the hall, get away from the noise, the machine, of course, is going printing out, and drink a cup of coffee. When he returned an hour later, he saw something unexpected and something that planted a seed for a whole new science. So the idea here is he's going to run his model, just like you run models in your Jupyter environment. And then he goes back and he runs the exact same thing again. Same input, you'd expect to get the same output. And that is a reproduction of the paper that he wrote on. Imagine this is pressure somewhere on his Earth. And there are two curves there. He typed in the pressure at the top there. That's the pressure. And let it evolve in time. He sees his equation starting to run, and the temperature goes up, or pressure goes up, and up, and up, and up, and falls down, and falls down, and falls down, and falls down. And he goes, okay, looks good. I'll come back in an hour. I'm going to go for a cup of coffee. And then he comes back, and he looks and compares with the simulation he just ran to the new output. This new run should have exactly duplicated the old. Lorenz had copied the numbers into the machine himself. The program had not changed. Yet as he stared at the new printout, Lorenz saw that his weather was diverging so rapidly from the pattern of the last run that within just a few months, all resemblance had disappeared. He looked at one set of numbers and then the other. He might as well have chosen two random weathers out of a hat. And his first thought, of course, is a vacuum tube is gone, because there must be a mistake. The calculator is wrong. The computer is incorrect. How could it be that you have the same program and the same inputs and get two different responses? So this is what these curves are, is they're going up and down, and they start to do something very different. So that after a while, the two pressures don't look the same at all. It's like throwing a ball with the same velocity, the same initial trajectory, the same position, the same coefficients of everything, and they land totally different locations. Suddenly he realized the truth. There hadn't been a malfunction. The problem lay in the numbers he had typed. In the computer's memory, 6 decimal places were stored. 0.506127. But on the printout, because he was printing these numbers out just to save space, only 3 appeared. 0.506. Lorenz had entered the shorter, rounded off numbers, assuming that the difference, 1 part in 1,000, was inconsequential. Now, this was a reasonable assumption. It's a deterministic set of equations. There's no random variable anywhere in here. A slightly different starting point, the weather should unfold in a slightly different way. The small numerical error was like a small puff of wind. And surely small puffs have to fade out and all cancel each other. So here's the implication. The implication of Lorenz's discovery is that he could have assumed that something was wrong with this particular machine or his particular way of doing it, or his particular code he'd written. And almost for sure, if you could come up with something that makes no physical sense, it is probably your mistake. I remember in the news a few years ago, someone came up with some experiment results that proved that they had measured something traveling faster than the speed of light. And they checked all the results and they went, wow, we found something traveling as fast as light. And then they published, we're publishing this, but we know it's wrong. Somewhere in here we made a mistake. We just can't find it yet. Lorenz probably should have done that. That would have been the sensible, logical thing to do. His equations weren't real weather. They were a parody of weather. They were an approximation of the physics. But he trusted that he at least had the physical relationships right. And so what this concluded for Lorenz is long-range weather forecasting was fundamentally doomed. There is no way you could have done it. So here's the background. We're in the 50s and 60s, right? Computers are coming around. We're in the space age. We're going to automate things. We're going to build bigger computers. They're going to run faster, and they're going to help us with everything. Where's your flying car? Right? This is the time period. There were decades. This was a decades of some pretty unreal optimism about weather forecasting. Newspapers and magazines were filled with hope for this weather science. You could do prediction, and if you could do prediction, well, then you could do modification and control. There were programs being funded by the government, such as the Global Atmospheric Research Program. The idea, the lofty goals of this is human society could free itself from weather's turmoil and eventually become its master. What you could do is you could build these like geodesic domes over cornfields and control where the temperature and the sun and the heat and the rain came from. You could have airplanes seeding the clouds to make it rain, adding just a little push in the right direction, and we could really control the whole system if we could know where knobs and levers are. Scientists would learn how to make it rain, learn how to make it stop. That's the ambition here. I'm going to go back to John von Neumann. This is the godfather of computing, as I said. We talk about the architecture of how machines are built as the von Neumann model of computing, the idea of putting the code and the data together in the same memory thing. He is at a central point of a lot of computing. One of his goals in his early computers was to not just predict, but to control the weather. That was the motivation. And what he did is he surrounded himself with meteorologists, included a lot of experts, and he gave breathtaking talks about his plans to the general physics community. He recognized that a complicated dynamical system could have points of instability, right? Critical points where a small push can have large consequences. So the idea here would be you got a ball pitched on the tip of a hill. If you knew where those points were, just by tapping that ball, you could make it roll down one side of the hill or the other side of the hill. With his computer up and running, if he could predict the state of the weather, von Neumann imagined the scientists would be able to calculate the equations of motion for the next several days. And then he'd have a committee of meteorologists who would send up airplanes and lay down smoke screens or seed clouds and push the weather towards the desired mode of oscillation. You know, bright sunny skies, not very much rain, raining only nighttime, no more storms. But von Neumann had overlooked a really important thing, and this is what this lecture is about, the possibility of chaos. That is, there's an instability, a point of where a small change could have a really large effect at every single point in the model. Now, weather forecasting in the 1980s had really grown. Von Neumann gave some big speeches, got government to spend big dollars create big expensive bureaucracies, and it basically was trying to fulfill out and live out von Neumann's mission. Well, the prediction part, not necessarily the controlling weather part. We were building increasingly large supercomputers that ran a model that at least physically had the same equations that Lorenz had, right? More equations, because we could solve more things. Rather than just doing 60 multiplications a second, which is more Lorenz's computer can do, these modern computers in the 1980s were doing millions of floating point operations per second. Of course, the computers you have in front of you do billions of floating point operations per second. Lorenz had been happy with just 12 equations, enough to get the flavor of the weather. The modern global models, 500,000 equations, and today that'd be easily 500 million equations. Basically the temperature and the pressure at every point along the globe. Big money was being spent on numerical weather prediction. Computer modeling has succeeded at changing the business of weather prediction from an art, something that a technician could do, to a science. And there were successes in short-term prediction that were statistically better than just flipping a coin, right? So you could talk about hurricane forecasting. So you just finished hurricane season. You know how they do those cones of uncertainty and they show you where it's going to go? We are actually able to predict the weather effectively several days out. We are much, much better. In the 1980s, but before out to about 2 or 3 days, even the best forecasts, though, were just really random guesses. And beyond 6 or 7 days, they're worthless. Today, we use bigger models, more computer. I think the 5-day, 6-day outlook is actually pretty good. And there's some scale out to 7, 8, 9 days out there. So you can actually sort of trust the weather sometimes. But by about a week and a half, forget about it. There's no model that can tell you what's going to happen. One of the observations here was something that is now coined the butterfly effect. For any small piece of weather, and for a global forecaster, if you're trying to figure out the state of this blue planet we're on, that could mean a thunderstorm or a blizzard. Any one prediction deteriorates fairly rapidly, right? I don't know where the storm's going to go. Errors and uncertainties are going to multiply, cascading through a chain of turbulent events. And what you're going to get is you're going to get little swirls like dust devils and squalls merging together. All their vorticity will merge together, and you're going to get these large continent-sized scale storms that you can sort of see from a satellite. One of the problems is weather models are limited with imperfect data to initialize the model. You don't have perfect data of what the initial conditions are everywhere. But let's say that we continue to move forward. The technology continues to improve. And when James Blake was writing this book in 1987, we weren't quite there, but we're pretty close. How many devices do we have in this room that can take sensor measurements? I got one. Anyone else got one of these things? Okay. These things have accelerometers and pressure meters and a whole bunch of things. You can imagine having one of these things spread out. Let's spread them all over the Earth so that these sensors, Internet of Things, are spaced 1 foot apart. And they're everywhere in the atmosphere. They're rising at 1 foot intervals all the way to the top of the atmosphere. And let's even suppose the technology here is this is giving accuracy to 1 in 10 to the 10, right? Perfect initial conditions. Imagine you had a system where you're able to measure everything and every other quantity meteorologists would like. And you could imagine a scenario where computation continues to get faster and faster. We don't just have our quad-core computers and our 8-core computers. I saw a report yesterday of a 64-core consumer computer. It's a 64,000 core computer. Okay, it keeps on going. And this infinitely powerful computer could take all that data and calculate what would happen at 1201, and then 1202, and then 1203. One of the implications of what Lorenz's work was the following. The computer will still be unable to predict whether Princeton, New Jersey will have a sun or rain day 1 month away. At noon, the spaces between the sensors will hide fluctuations the computer doesn't know about, tiny deviations from the average. But at 1201, which is 1 minute later, those fluctuations will have caused little errors about a foot away. And very soon those errors will multiply to a 10-foot scale, and then a kilometer scale, and then a continent scale, and a globe scale. This idea that the errors in a system are going to grow all the way through. Now, for experienced meteorologists, this idea that a small change is going to cause a big impact runs against all intuition. One of Lorenz's oldest friends was Robert White, a fellow meteorologist at MIT, who later became the head of the National Oceanic and Atmospheric Administration, NOAA. Lorenz told him about the butterfly effect and what he felt it meant for long-range prediction. White, his friend, gave von Neumann's answer. Prediction? Nah, this is weather control. This is what we're going to do with this. His thought was that with small modifications, well within the capability of humans, would cause the desired large-scale effect. So this is the idea, right? So the concept and the idea is Lorenz was saying that the problem that the butterfly effect is giving you is you're not going to be able to predict what's going to happen at all. What other people were hearing was, oh no, this is great. That means that with a small little modification, I can bird flapping its wings in Japan causes a tornado in Oklahoma, that kind of thing, right? But the idea was you could do these sort of little changes everywhere. That's how this idea was being viewed. But Lorenz didn't think about it that way. Lorenz thought differently. Yeah, you're right. You definitely could change the weather. You seed a cloud there, or build a geodesic dome here, or flap your wings. I agree that what we're saying here is it could actually change the weather. You could make it do something different than it wouldn't have done before. But if you did, you never know what it would have done otherwise. It'd be given like an extra shuffle of an already well-shuffled deck of cards. You know it'll change your luck, but you don't know whether it'll be for better or for worse, right? So this idea of the butterfly effect was viewed as a way of having control on a system. And what Lorenz was realizing was it just means we don't know anything in terms of long-term outcomes of these kind of systems. So just another one on the butterfly effect. I happen to like this comic, so I'm just going to take it aside and give it. And in sort of programming, we're doing a lot of programming here. In programming, you know what a text editor is? You're using Jupyter right now as a text editor kind of interface, but you could use another program, which is a text editor. You use a text editor. What do you use? Oh, it's an IDE. Which one? IDLE. You use IDLE. Well, programmers have debates over which is the best IDE or text editor to use, right? So if you go into a Linux system, you might hear the word Nano. Nano is the one for text editor for people who don't actually really know how to use text editors, or at least that's what a real programmer would say, because real programmers use Emacs. Now, Emacs is a complicated language. It's got a lot of like Control-M, meta-Q type things, but there's menus and stuff. Real programmers use a language called Vim. Now, Vim stands for visual programming or visual I, and it doesn't have any menus at all. What you've got to do when you're programming with Vim is you just see a screen of characters. It's all text, and you just type in codes to tell whether or not you're going to enter data or remove data. There's no menu, there's no mouse, there's no anything. It's just by entering certain things in. So if you want to type something in, you hit I to start typing, then you type, and then you hit escape to stop. And if you want to delete the next 3 lines, you type in D3D for deleting 3 lines. So real programmers use Vim. No, real programmers use cat. Cat is a Unix line command tool that the real programmers use ed. I got to do the joke. Ed is one based on the idea back in the day when you had limited screen real estate. And your screen could only show you 1 line. So ed was a line editor. Imagine not being able to see your entire program, but the only thing you could see was a single line at a time. Ed would be a programmer that could work within that. No, real editors use cat. Cat was a program allowing you to type with one go all the way into a program without editing at all. You're not allowed to make any mistakes. Write once, type it all through. No, real programmers use a magnetized needle and a steady hand, and they just flip the individual bits all the way through. No, excuse me. Real programmers use butterflies. They open up their hands and let the delicate wings flap once. And that disturbance ripples out into the clouds, displacing the flow of the eddy currents up in the atmosphere. And that causes momentary pockets of high pressure, which acts as a lens, which deflects in the incoming cosmic rays to flip the bits of the computer. Oh, nice. Well, you know, there's an Emacs command to do this, and this is a joke about Emacs. Oh yeah, good old Control-X, Meta-C, Meta butterfly. Damn it, Xmas. Doesn't matter. I like the comic. It's a computer thing. Anyway, my point being, the idea of the butterfly is these small changes cause large changes in the result. The way we understand this butterfly effect is a small change in the initial conditions can have a large impact on the eventual outcome. Lorenz's discovery of this phenomenon, that you could have not just at critical points, not just a ball rolling down a hill, but everywhere in the dynamical phase space of the problem, at any position, at any temperature, at any pressure, you could have this small changes cause a large effect. This discovery was bigger than just that numerical weather prediction was unpredictable. He had stumbled on a link between aperiodicity, that is things that look like repetitive, but they're not actually periodic, and unpredictability. Nature is full of other examples of systems that have this. Animal populations that rise and fall, they sort of look regular, but they're not. Epidemics that come and go, they look regular, but they're not. And any other kind of repeating pattern that was never truly periodic. Yes?
So, would that change when we have quantum computer?
No.
Because we will be able to talk to one.
That's right.
Would the error be smaller?
It doesn't matter. What Lorenz has discovered is it has nothing to do with how you solve the problem. The equations themselves are inherently chaotic. Solve it perfectly, you're still going to get this behavior. Now, the butterfly effect, this idea of small changes, now it has a technical name. The technical name would be sensitive dependence on initial conditions. Some also sometimes called a chaotic solution. But this is not really a new notion all the way through. There's a proverb that sort of gets to this. For want of a nail, the shoe was lost. For want of a shoe, the horse was lost. For want of a horse, the rider was lost. For want of the rider, the message was lost. For want of the message, the battle was lost. And for want of a battle, the kingdom was lost. So in life as in science, it is well known that a chain of events can have a point of crisis that can magnify small changes. Okay? So this is not that surprising. The surprising bit is those points of crisis are everywhere in a chaotic system. There is no one special moment. Every moment is special. Chaos means that such points are everywhere. They were pervasive. In systems like the weather, sensitive dependence on initial conditions was an inescapable consequence of the way scales intertwine with the large. As things interact with each other, those points of instability occur everywhere. Now, Lorenz took this idea and this thinking about his 12 equations and the fact that he could see this instability just by changing the coefficients or the initial conditions a bit, and tried to reduce it down to the smallest set of equations that he could find that produced this complex aperiodic behavior. It doesn't going to be the same, but it's going to have sort of fluctuations. It's based on a system of 3 nonlinear equations, and it's inspired effectively by a convection problem. A physics involving fluid convection. So Lorenz took this simpler set of three equations. Basically, it's convection stripped down to its essence, and throwing out everything that could be extraneous, making it unrealistically simple. This is a very simple system. There's basically nothing left for the weather model, but he left nonlinearity. Nonlinearity is when the terms in the equation depend upon their variables as squares or as sines or as cubes or something that's not linear. In the eyes of a physicist, these equations are easy. Here's the equations in the Lorenz model. And the question is, could you solve that? Okay? Sigma and B and R are just constants. You've got three derivatives, x, y, and z. And the derivative of x depends upon the difference between y and x. The derivative of y depends upon that linear combination of x, y, and z. And the derivative of z talks about that multiplication of x times y combined with z. So could you, this is a rhetorical question, could you numerically solve these equations? How would you attempt to solve these equations? Not make it rhetorical, let's make it actually precise. If I said solve these equations, what would you do? Given that you've had 8 lectures so far in this class. Yes, yeah. You'd use an algorithm. That's right, right? So you'd rewrite the derivatives as a finite difference, and then you'd have rules to update what x, y, and z were all the way through. Okay, so this is a bit of physics. One of the things I need you to be able to do at this point in the course, if I give you a set of equations like this, you go, okay, I know how to implement that as an algorithm. I know how to rewrite that as a set of finite difference equations and use something like Euler's algorithm, Euler's method, to write the code that would solve that. Okay, let's take a look. I went and did this. This particular set of equations, it's a convection problem, but can actually is the same set of equations by something called a water wheel. This set of equations is basically the same mathematics as this system. Imagine you've got a wheel, okay, it can spin around. The wheels has a bunch of buckets, containers, cups all the way around them, and the containers are leaking. There's a stream of water filling up these buckets, and because the buckets, which are on pivots, and the whole wheel can go, as soon as it loses a little bit of, there's a bit of torque due to gravity, the wheel can start to spin towards the left or the right, and the next cup along the line will start filling up with water. Well, there's friction in the system as well, so it doesn't spin forever, and these wheels, this water starts to drip out of the buckets. So after a little while, it is entirely possible, and it does happen, that the wheel starts to turn a little bit to the right, and it flips back and forth and back and forth. So let me see if this is going to work here. Let's just see if we can find a nice little, we can get an ad. What we're going to get. We're going to see what we get. Let's see if we can see this water wheel. Or we're going to get nothing. Ooh, there we go. So can you see the cups all the way in there? So that's just water filling up a plastic cup. And you can see that the wheel is made up look like a skating wheel from a roller skates. Yeah, my guess is looking at it. It's just because you're looking at it. We don't have the lights off in the room. Okay, but all you're looking at is a wheel spinning to the right, spinning to the left, and sometimes it spins, and then it keeps on spinning, and sometimes it turns around and goes the other direction. You understand the dynamics? So the variable you may want to plot is the angle this thing is rotated to. Okay, so if it's rotating quickly, slows down, goes quickly again, goes quickly again, and then every once in a while, we'll go the other direction. Right? So this is sort of a periodic motion, but it's not perfectly periodic. See how it's going the other direction? Okay, so what we're trying to predict is 5 minutes later, what the position will be of this wheel. Does that understand it as a physical problem? Okay, so it's just how fast it's spinning, left or right. The rate of flow of water in, which is coming up here, is known. We know the rate at which the water is leaking out of the cups. We know the coefficient of friction. Predict the rotational velocity or the direction of this wheel turning forward in time. This is an example of a water wheel. Okay, so if we got a water wheel, oh no, this is not good. Good. Back again. Okay, so that system of equations, I said it's actually convection is the equations, but the same model comes up with this water wheel. You're trying to predict whether or not the wheel is going to go counterclockwise or clockwise, and that will change over time. So this Lorentzian water wheel is what those equations do. Water's pouring at a steady rate, and the flow of water from each cup on the water wheel is slow, and the top water bucket never fills up enough to overcome friction. Right. If the water is coming in too slowly, then the water will basically drip out and the thing will never start to spin. But if you get a critical flow, as long as it's flowing fast enough, you'll set the wheel into motion. And this water wheel can settle into rotation that continues either at a steady rate, or will speed up and slow down, or spin to the right or spin to the left. And over long periods of time, the spin will never settle down. Now, the variables here are basically the rate of rotation, the angle of what it is, and then something to do with how much fluid is inside the, I think it's probably the moment of inertia or some quantity like that of the overall system. That, taking these three equations, x, y, and z, and solving this equation, you get that picture. Now, I don't know if you've ever seen that before. That's called a strange attractor. That's sort of the classical example of a Lorenz attractor. It's typically associated with the word chaos. I believe this book that I'm sort of telling the story from, the front cover, has an animation of what this is on the front. This is the solution to this system of three equations. Again, the system of three equations are just three derivatives, and you could solve them. So let's do that, right? I'll come up with the text at the end. Let's solve this numerical model. Well, even if you did the simplest thing, Euler's model, that would say turn each one of these derivatives into a rule that would let you evaluate the next value of x from the previous value of x, y, and z. This is Euler's algorithm applied to this set of equations. Okay? Specifically, in his paper, he used those as his constants, so we can write code that would solve this. The code is basically going to be having to iterate through these equations. So I've got to initialize it. Let's initialize it with x 0 equals 1, y 0 equals 0, z 0 equals 0. What I'm going to do is every time step, I'm going to pass back the current values of x, y, and z. And as long as the simulation is not over, I'm going to update it with Euler's model. Now, this is only slightly different than what you've seen before. Euler's model always has to have the new version of x, y, and z depend upon the old version of x, y, and z. Because these three equations are coupled, I can't go and update this variable right here with the same name because I want to use the old value of x down here, and down here. So one way of getting around that is I create new variables called x new. So this is the new value of x, the new value of y, the new value of z. These are all the old values. And then when I've updated them, then I swap them in. The old value of x is now the new value of x. And repeat the loop. Once we run that bit of code, we want to plot it. Let's just plot the angle of this water wheel as a function of time. Okay, and I'm going to run that code. So this is representing something about the water wheel spinning. Okay, it might represent its angular velocity, say. So it's quickly it's spinning generally in a counterclockwise direction, spins in a clockwise direction, counterclockwise direction, clockwise direction, counterclockwise direction, clockwise direction, counterclockwise direction for a while all the way through. This is that aperiodic sort of, it's not random, but it's not periodic kind of motion we're looking for. And here's what I want you to do, okay, exercise. I want you to modify that code. So even if the initial conditions are very similar, show that the two solutions would depart. And this is really, really easy. I've done this for you. All we are doing is having the same code, and rather than having the initial condition being 1, 0, 0 for the three values, it'll be 1.0001. Y equals 0, 5. So that one small change, you can see that at the beginning, the two solutions are completely overlapping. By about 30 seconds though, these two solutions, which so looked that they were basically the same, are doing something completely different all the way through. This is an example of a chaotic system, sensitive dependence on initial conditions. If you make the equations exactly the same, then you get the same results. It's not random. I can run this program every time and always get the same position. But if I make the smallest change in the initial condition, doesn't matter how small it is, you will get a different long-term behavior. So your prediction might be okay for a while, but it's fundamentally limited. It can never do it. Weather's like that all the way through. This idea, because it's three variables, I'm just plotting Z versus T. We can plot Z and Y and X all together, and we can do this with a 3D plot. So we've done this before. There's a 3D plot. We've seen this how to do it. Import X as 3D, and then once you've done that, you can create a plot which has a 3D projection, and it understands three variables you can plot against, and you get the classic butterfly curve, Lorenz attractor. It's called a Lorenz attractor because it's not a random pattern. It's just sort of focusing around these two dominant circles. This is basically clockwise motion, counterclockwise motion. Clockwise motion, counterclockwise motion. It doesn't matter where the model starts, okay? You can start this model anywhere you like. I can start it, say, right here, and it will converge to and rotate around these two different cycles, called Lorenz attractor. Takeaway. Years later, the physicists would give wistful looks when they talked about Lorenz's paper on these equations. They'd say things like, that beautiful marvel of a paper. By then, and then being by the 80s, it was talked about as if it was an ancient scroll preserving secrets of eternity. In the thousands of articles that made up the technical literature of chaos, few were cited more often than deterministic non-periodic flow. That's the name of this paper. For years, no single object would inspire more illustrations, or even motion pictures, if you've seen those, than the mysterious curve depicted at the end of the double spiral that became known as the Lorenz attractor. For the first time, Lorenz's pictures had shown what it meant to say, this is complicated. All the richness of chaos was there. Few laymen realized how tightly compartmentalized the scientific community had become. A battleship with bulkheads sealed against leaks. Biologists had enough to read without keeping up with the mathematics literature. For that matter, molecular biologists had enough to read without keeping up with the population biology literature. Physicists had better ways to spend their time than sifting through meteorological journals. Some mathematicians would have been excited to see Lorenz's discovery. Within a decade, physicists, astronomers, and biologists were seeking something just like it, and sometimes even rediscovering it for themselves. But Lorenz was a meteorologist, and it took a few decades, and no one thought to look for chaos on page 130 of volume 20 of the Journal of Atmospheric Sciences. So if you're ever interested, it's not actually that hard a paper to read. It was published in 1963 in the Journal of Atmospheric Sciences, and it's one of the top 100 papers ever cited, ever. And this is where he solved this set of equations and introduced this idea of the butterfly effect and chaos, the beginning of a field of science all the way through. This idea occurs in lots of physical systems. Here's another physical system which it occurs in. Nonlinear pendulum. Now, if you did the lab on Tuesday, you've already done this. If you're going to do the lab this afternoon, you're going to see this. What I want you to do in the lab is solve an equation, a system, for a damped, driven, nonlinear pendulum. That's just a pendulum forcing back and forth and back and forth, but someone's pushing it, giving it kicks all the way through. And I want you to solve it where it's nonlinear. Its acceleration depends upon the sine of the angle, damping parameter all the way through. Now, if you do this thing, I'm asking you to explore different parts of its behavior. What I'm going to do is jump to the end here and just do something with my version of the solution. You'll be able to do this as soon as you're done the lab or right at the end. The idea being, this is showing you what a pendulum is doing. Imagine a pendulum swinging back and forth and back and forth. That's being forced with a certain external force. So if I don't force it at all, if I have A equals 0, and I give it an initial perturbation of 0, what you're going to see is the pendulum swings, starts at the right, goes left, right, middle, stop. It's damped. If I give it a bit of a push, okay, this is setting the amplitude. The thing is going to swing back and forth at a period given by whatever I'm forcing it at, the forcing period. If you can see right here, this thing is moving from an amplitude of plus 0.3 down to minus 0.3. It's the combination of how close the frequency is that you're forcing it to the natural frequency that gives you the response. But generally, if I force something at a higher amplitude, I'm pushing it harder, my scale gets larger and larger. If I push it at 1.0, okay, it's now swinging quite far. Now, I want you to remember, though, that a pendulum can only ever swing so far. If I take something which is a pendulum, I want to really break this up. Anyways, there's a pendulum, right? Here's swinging back and forth with a period or an amplitude of 1 radian, right? Whoa. There I'm swinging it with more than 2 pi radians, right? So when I swing it like that, I've gone all the way around the circle. I'm outside of a bound of plus pi to minus pi. So if I really start swinging this thing quite a bit, okay, I can get in a cycle where it's constantly swinging all the way around. This is basically just giving something a push at the right frequency so that you push the pendulum all the way around, so it never stops. I could give it a different kind of frequency and get, well, that's sort of boring, and get a different set of behavior, right? So now I'm pushing with a strength of 1.1, and the pendulum swings back and forth, but then gets to a low where it's sort of spinning off in one direction all the way through, back. It's sort of swinging, it's going around, it's oscillating, but it's also spinning, going all the way around. Now, for a pendulum, we want to keep it tracked. We want to sort of say what its rotation is between 2 points. So what I can do is I can clip it. I can basically say whenever the position gets to plus pi, that's exactly the same as minus pi. And in the code for the lab, I'm giving some code that does this. Sometimes you call that clipping. This is just folding this all over. So this fits always within a plus pi to minus pi range. But you can uncomment those lines if you want to. This is just the pendulum spinning all the way around the circle. Now here's the thing about this forced pendulum. It's spinning around and left and right and left and right. Here is the exact same model. Okay, with the exact same parameters, with a very small difference in the initial displacement. This is setting up a pendulum. I'm going to push this at the same frequency and the same amplitude, but one pendulum starts 1 in, is that 100,000? 1 in 100,000. We're talking a micrometer, a micrometer difference in its initial amplitude. And we're going to let this go for a few seconds. Can you see how the two pendulums would behave exactly the same? You'd see these two pendulums moving back and forth, being forced with the same external conditions, and for all intents and purposes, starting off in the same position. But after a minute and a half of swinging, one of the pendulums would start having a different cycle all the way through. It would go on a different trajectory. It would have spun a different number of times. In terms of looking at it in the cross section, This is being clipped all the way through. The time histories are completely different. Nonlinear damp-driven pendulums are chaotic systems. What a chaotic system is a system that has sensitive dependence to its initial conditions. And what it means is you have a point of instability, as in the solution will not stay bounded, but it still won't stay near to it everywhere in the phase space. Those are chaotic solutions. Okay, so what I was trying to get across is this quality of some numerical problems, of some equations of physics, inherent in the mathematics of the equation. Nothing to do with solving it. You could solve this perfectly, and you would get this effect. This is the reality about a lot of the physics and a lot of the science we work with. It is not deterministic. Not because there's any randomness in the world, but the equations themselves have very subtle dependence on everything that's going on. Okay, so just to finish it off then, that's what I want to talk about was Lorenz tractors. This afternoon, we're going to finish off lab number 3 for those who have not done it. I did promise that I would spend a few minutes talking about the test. We're doing a test on Tuesday, right? I did begin to draft this up so I can tell you what I've got written up so far. You are encouraged, welcome, allowed, permitted to bring in a single piece of paper, 8.5 by 11, this kind of size. If you write on it, that's fine. You can use 2 sides if you want. If you really wanted to type something out, I guess you could. I'm not recommending that. I think just handwriting it out would be just fine. Of whatever you would like to gather from the first 8 lectures and the first 3 labs and the first couple assignments. In terms of structure, I'm thinking sort of 3 questions. And what I'm really trying to examine is, can you take a physical system and understand this idea of what the equation of motion is? So let's be concrete. Here's a lab. Here's an equation of motion. Okay? That could be on the test. I didn't put this one on, but it could be. There is an equation of motion. I might ask you to implement Euler's algorithm to solve that equation. How would I do that? I would give you this code. It would have all the pieces of it. And then just this section, I would white out this part, this point, this part, this part, and this part. Now, Euler's equation is even simpler, right? I would just leave blanks here, 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 here. So what would you be expected to do? Code up the right part all the way through here. What's another thing we could ask? If we go down to lab, that's one, lab 2. I sort of see if I can have an example here. That was lab 1. In lab 1, we were talking about a skydiver problem. And aha, here we go. There was an equation of motion, right? We studied this one. This is an object falling under quadratic drag. And what I asked you to do was rewrite this as a system of equations, 2 first-order equations. Now, what I wanted you to do is edit the LaTeX. We're doing a pen and paper exam. You don't need to know the LaTeX. You can write it using math notation. But the idea is to write down the pair of equations that are the first-order equation equivalents of that. So what would be the answer to this problem? dv dt equals minus g plus k of y over m times b squared dy dt equals done. Yes?
Wait, so the computer is not, this exam is not a computer exam?
It is not a computer exam. Yeah. It has been a computer exam in the past. I just don't want anyone to get caught up in some bug or some error, because I just don't need you to, I don't need you to practice your debugging skills. Yes, yes. So you would code. So I'll try and be like very specific. Okay. So let's imagine that this was the problem. Okay. Part A might be write those 2 equations down if I tell you that. Does that make sense? Part B would be Euler's method. because I want to make sure you understand Euler's method. And I would give you this. Marker. And the idea is, what 3 lines of code, math, code would go in those blanks? Does that make sense? So we can do that together, right? So just from here, if you know Euler's method, the idea is you have to rewrite that so that the change in y is equal to v. So all that we're writing is that. This thing is just saying it's going to be equal to v write down that. I need to write down that. So you're coding by typing, but that's all heavy typing. Well, whatever we covered. Yeah. In the sense that, so that's Euler's method. So can you go from a physical system to these equations? Can you write down the equations of motion for things we've studied? Right? So I could describe a problem and have you write down the equation of motion for something like start with F equals ma and add in a drag or a spin or something like that. Like if I give you the forces, right? So another variation of the problem is I could give you some forces. So what are some forces we talked about? Okay. Do you agree that those are 2 forces? Right? Okay. Okay. If I give you 2 forces and I say, starting with Newton's second law, write down the equation of motion. All I'm looking for is second derivative, which is the acceleration, is equal to g that'd be it. Does that make sense? Right? So what you're doing is you're translating the physics into an equation, or from the equation into 2 equations, or from the 2 equations into a numerical model. Okay? And what I'll do is I'll give you this code in the context of an app and everything else, but I'll write all that out. And I think what I'll even do is I will show you the output of the model as if this was to work. I just want to make sure you can do this part. Now there's 3 methods we've been talking about, and in the lab, we sort of in the little assignments, we've only been focused mostly on Euler's method. Please take a look at the previous 2 lectures. We've talked about Euler's method, Euler-Kromer method, and Euler-Richardson method. Okay? So there's 3 different ways of solving those. You're solving this lab you're doing right now for me today is using Euler-Richardson. Make sure you understand it so that if I ask you exactly the same question, and left you blanks, you could put whatever you need to put there, right? All the way through. So the 2 kinds of problems are on 1D and 2D projectile motion, basically things, particles moving under forces. And the other kind of thing we looked at is oscillators, spring mass systems, pendulums, other kind of oscillators, right? Those are the 2 sort of types of physical systems. And what I'm trying to just assess, my test plane thing is, can you go from the physics through the math to the code and fill in the blank somewhere in there? The only bit of numerical analysis we talked about at any length is the idea of errors. That is the difference between a numerical solution and an analytical solution, and how the error depends on the time step. So at one level, If you have a numerical model and it has a lot of error in it, what is one way of reducing the amount of numerical error with Euler's method? Great, check, easy. Decrease the size of the time step, right? The more advanced version would be, how is the error depend upon the size of the time step? But the basics is, do you know that if things aren't working, just to make the time step smaller? I have in my mind 3 different physical problems, asking questions in this sort of range. So, trajectory motion, particle motion, motion of things in 1, 2, or 3 dimensions, but basically particles, and oscillators, pendulums and springs and other types of oscillators all the way through. And 3 different numerical methods: Euler, Euler-Kromer, Euler-Richardson. No graphing, plotting, computers required. Maybe you don't have to bring in a sheet of paper, but you're welcome to. So have a copy of Euler-Richardson nearby. You just got to translate it. You just got to implement it with that code. No issues with computers running away. No issues with computers not functioning. I will be in the room with you on Tuesday, so I can collect the physical piece of paper from you. That's my plan. So how are we doing? Any questions about content we've done up to this point in the course or the test? Yes. There is nothing you are not allowed to put on. You can, whatever you can put on the piece of paper. There's no restrictions on the piece of paper. Yes. Yes. Sure. Well, so chaos is a description of a system for which a small change doesn't remain small. Okay. Now, lots of systems have critical points. Okay, in the sense of you try and balance this on your fingertip. Okay, it will fall this way or this way. That's not a chaotic system. Okay, a small deviation from positive to negative will cause a really big difference. That's called a point of instability. A chaotic system would be one where at every location, like any initial orientation, like if I'm here with a pen, it is always going to fall down. It's always going to fall this direction. In a chaotic system, if I move this, change this in any way, how it evolves will be completely different. So those critical points, those instability points are everywhere. Well, as tiny as you want. Now, so when you study, so this science is now given. You wouldn't take a course called chaos. You take a course called dynamical systems, and what you would learn is the difference between these two solutions. This error is going to grow like e to the power of something like an exponential difference. It'll grow depending on what the difference is between these two initial conditions. If they're really, really small, it will take longer for it to diverge. If the errors are big, they diverge very, very quickly. So there's a mathematics behind all this as well. But the point is, these occur in physics systems. Yes. No. I guess I could, but no, I'm not taking your shit afterwards. Like, as long as it's your work and you're doing it, and you're not like communicating with your neighbor, using hand signals, or I don't know how you communicate with them. As long as it's you, that's just fine. Yeah, but I also don't want you to bring in like. Should I say the obvious? I'll say the obvious. Please do not think you have prepared for this because you figured out a way of printing out every sheet of the lecture as little small boxes on one sheet of the paper. Okay? Laughing, but I know some people who have that as their thought, like, oh, I know what I'll do. I'll make it so that little tiny boxes. Don't do that. Most of the lectures are the same story again and again and again. Reduce what we've done down to a page or two of notes. Mechanical systems, 3 numerical methods, and that's what I'm going to be asking you about on Tuesday. Okay, if you've already completed lab number 3, I will see you on Tuesday. And if you got to get into lab number 3, I'm sort of around. Kyle's back in the room to assist you. I can also talk about anything else we need to talk about while I am physically here. Okay, great, thanks.